This lesson is about solving problems having to do with resistance and Ohm's law. Let's start off with a little refresher on what resistance is. Remember, it's just a measure of the difficulty of electrons moving through a circuit or through a conductor. So it's how difficult it is for electrons to move through a conductor. It's measured in the unit of ohms, and so it's this Greek letter omega that represents ohms. And the equation that we use is Ohm's law, and that states that resistance is equal to the voltage divided by the current in a circuit. Let's go to some questions now. Okay, practice problem 1. 10,500 ohm resistor is placed in a circuit with a 15 volt power supply. What will the current be in the circuit? So we know we're going to use Ohm's law because those are the things involved. So I'm just going to write that down. So R equals V over I, right? We know that we're going to use that equation. So we need to know two of these things. And we're given in the question, we're given this 10,500 ohms. And what variable is that? Well, we know that's the resistance because it's in ohms and it refers to how resistant that is to the flow. And then the 15 volts, that's pretty obvious. 15 volts is our potential difference, right? So we're trying to solve, in this equation, we are trying to solve for the current, for I, right? Now, in order to solve for I, what are we going to have to do? Well, you can sort of cross-multiply the I up to the R, or just switch the places of the I and the R, whichever way you like to look at it. So essentially, this equation is going to become I equals V over R, right? Now, we know that V equals 15, and R equals 10,500 ohms. We should put our units in there too, 15 volts over 10,500 ohms. If we use these base units every time, it's pretty easy to see the unit that comes out is just going to be the current in amps. So 15 divided by 10,500 gives us a pretty small number, 0.001429, right? And again, since we're working in all base units here, the base unit for current is amps, right? So this number is pretty small. So it might be easier to express it as milliamps, such as you see in this answer up here. Remember, a milliamp is a thousandth of an amp, right? So in order to turn that into milliamps, we can just divide by 1,000, in which case we get approximately 1.43 milliamps, right? I just rounded in this question, this answer I rounded to 2 significant digits instead of 3, but either way, it's fine. So about 1.4 milliamps. So very small amps, and that's very small number of amps, and that's because the resistance is so high, right? So it's going to resist more current, and that's why the current is so low. It's just a small number. So in this next question, we're asked to draw where we put an ammeter and a voltmeter in our circuit. An ammeter, remember, goes along the flow or along the conductor, along the wire, and all it's going to do is going to measure the flow along that wire. So we would put our ammeter something like there. A voltmeter, on the other hand, we wouldn't put it in line with the circuit because a voltmeter wants to measure the difference, the potential difference between 2 points. So if we wanted to measure the voltage across the resistor, we would hook up 2 wires on either side here and put the voltmeter here. So the voltmeter is basically testing the voltage on each side of that, and it would tell us what the voltage difference is between those 2 points. So basically it's telling us what the voltage of this resistor is, right? So that's the answer to A. B says label the direction of electron flow. We know electrons flow because electrons are negatively charged, right? So they're going to be attracted to the positive terminal of the battery. This is our battery over here. It's a VS, I think stands for a voltage source, which we can just consider a battery. So it's going to be going this way, right? This is the direction of the electron flow because it's going to go towards that positive side. There you go. If you wanted to draw it down here too, it would be going this way down here, right? So it follows this loop going this way. We know that. So now, let's pretend in this circuit that we've created, we look at our voltmeter and our ammeter, and we get that it's 0.2 amps and 15 volts. Could we use that to find the resistance of the circuit? Or the resistance, particularly of the resistor in this case? Yeah, we can, right? We have Ohm's law. And Ohm's law once again states that R, oops, let's do that in blue, R equals V over I, right? Now let's be careful about this question. What are we given? Is everything in base units? Yep, so we're given that the current is 0.2 amps and that the voltage is 15 volts, or the potential difference is 15 volts. Those are already in the base unit, so we don't even need to convert anything. We don't need to rearrange the equation at all. We can just plug everything in, right? So if we do that, the volts is 15 over 0.2. What's that going to give us? Well, if we do that math, it's just going to give us 75. And remember, the units for resistance is ohms. So we would draw it like that. There we go. That's our answer. So we could actually use just a voltmeter and an ammeter to determine what the resistance of that resistor is. So this next question has to do with passing voltage through human skin. Not something you necessarily want to try. But if you placed a 9-volt battery, like a 9-volt battery with the 2 prongs on top, if you place that against human skin, the skin has a resistance of 100,000 V. I think that's wrong. The question should say, make this correction, should say the resistance is 100,000 ohms, not volts, right? Because the battery is 9 volts, and the resistance of skin is actually pretty high. Dry skin, at least, is pretty high. So that makes sense. So if you were to touch the 2 prongs of the battery with dry skin, don't try this at home. No, don't try playing with electricity at home. But if you were to do that, what would the current be going through the skin? So again, the 3 things we have here are resistance, voltage or potential difference, and current. And when we have those 3 things, we can always use Ohm's law. So resistance equals potential difference over current. What are we given in the question? Well, we're given the resistance of skin is 100,000 ohms, right? Put a comma in there. And we're given that the potential difference is 9 volts, right? Because it's just a 9-volt battery. So again, we can just plug this in. Now this time we're trying to solve for, what are we trying to solve for? Well, we're trying to solve for current, right? So in order to solve for current, we need to rearrange this. It's actually like the first question we did, right? So we can rearrange this by just cross-multiplying these 2 things or switching the places of those 2 things. And when we do that, we're going to get that I is just equal to V over R, right? And then if we plug the numbers we know in, 9 divided by 100,000, is that the right number of zeros? Yep, it is. So 9 volts divided by 100,000 ohms. It's going to give us probably a pretty small number. So my calculator actually says 9 times 10 to the negative 5, which is like saying 0.00009. Very small number. In my answer here, I put this funny little symbol. That means 90 microamps. So that little u, it's actually a mu, it's a Greek letter, and that means microamps. And there's actually 1,000,000 microamps in an amp. So what this basically means is 10 to the negative 6. That's sort of the factor for that microamps. But this answer here gives us amps, and I'm okay with that if you keep it as amps. Or if we divide by 1,000, we can get that into milliamps, right? So that would be we take away 3 of the zeros basically, 0.9 milliamps. The point is, this is a very small number. Or if we divide by 1,000 again, we can get it into microamps, right? But the point is, this is a very small number. So putting a 9-volt battery against your skin, 0.09 milliamps, you're not going to feel that because that is so low. You only start feeling stuff around 1 milliamp, right? So this is why it doesn't actually hurt when you touch a 9-volt battery to your skin, because the current, there might be a little bit of current passing through there, but it's so small that it's not going to actually hurt you, or you won't really feel it. Obviously, if you have wet skin or you put it to your tongue or something like that, again, do not try this at home. But if you were to try that, the resistance would be a lot lower because water, especially water with salts and stuff in it, carries electricity a lot better than dry skin. So the current going through there would be a lot higher if that was the case. So what I want you to do now, I want you to try questions 4 and 5 yourself. I'm actually not going to go through the solutions to those because I think you can handle them. I think you're capable of doing that. So just to get you started though, question 4 requires us to calculate the potential difference or the voltage required for a defibrillator machine, you know, the ones that can restart your heart if it starts beating funny. So the key to these questions is to make sure that our units that we're using are the base units, right? So 17 milliamps, is that the base unit for current? It's not, right? We want to get that into amps first. This 100,000 ohms, we're okay there. Ohms is the base unit. But make sure you convert that amperage into amps instead of milliamps before doing this question. Same thing with question 5. That's sort of the trick there. Make sure you're converting before you do it. 5b has you thinking about why your answer might not be exact. And think about it. See if you can come up with an answer. We'll discuss it in class if you can't. All right, there you go.